touch-tone phones. Please ensure that your lines are unmuted and please record your name when prompted so that I may introduce you to ask your question. The conference is being recorded, and if you have any objections, you may disconnect at this time. Please continue to stand by. Our conference will begin momentarily.
Hello, everyone. Thanks very much for joining us for our media teleconference today. I'm Elise Fisher with NASA's Office of Communications, and we're here today to discuss NASA's Ingenuity Mars Helicopter. Ingenuity was the first aircraft to make a powered, controlled flight on another planet, and now, after nearly 3 years on Mars, it has flown for the last time. So we have speakers here today to share more, discuss a bit about Ingenuity's many accomplishments, and answer your questions. So we'll first hear briefly from Laurie Glaze, Director of the Planetary Science Division at NASA headquarters, Laurie Leshin, Director of NASA's Jet Propulsion Laboratory, and Teddy Tzanetos, Ingenuity Project Manager, also at NASA's Jet Propulsion Laboratory. After their remarks, we will then take questions from media who are listening on the phone lines. And I'll note that for that Q&A portion, in addition to those speakers, we will also have Dave Lavery, who's our Ingenuity Program Executive at NASA headquarters, also on the line. But first, I will turn it over to Laurie Glaze to start us off. So please go ahead, Laurie.
Great. Thank you, Elise. Good afternoon, everyone, and thank you for joining us today. While we knew this day was inevitable, it doesn't make it any easier to share that today the Ingenuity Mars Helicopter's flight operations on Mars have ended. Ingenuity was truly an all-of-NASA mission. It cut across science, technology, human spaceflight, and aeronautics. It was designed as a technology demonstration, expected to fly no more than 5 times over 30 days, but it's ending its mission having completed 72 flights in just under 3 years. It's almost an understatement to say that it has surpassed expectations. Ingenuity is a 4-pound rotorcraft. It had a sole objective to conduct test flights in the thin atmosphere of Mars and collect important engineering data. But it has gone way beyond test flights and has laid a very solid groundwork for future aerial exploration on Mars and beyond. In 2020, when we launched Ingenuity with Perseverance, we were hopeful that Ingenuity would open new possibilities and spark questions for the future about what we could accomplish with an aerial explorer. We asked ourselves whether a helicopter could scout ahead for rovers and help plot the most efficient course for the best science. We asked ourselves whether a helicopter could support future human missions with aerial capabilities. And during its 3 years of operations on Mars, I am just really thrilled to say that Ingenuity absolutely shattered our paradigm of exploration, introducing this new dimension of aerial mobility. I couldn't have summed up the importance of Ingenuity and the lessons it's taught us any better than Vanessa Rupani. Remember, she was the student who named the helicopter in 2020. And in her words, in Vanessa's words, the ingenuity and brilliance of people working hard to overcome the challenges of interplanetary travel are what allow us all to experience the wonders of space exploration. So thank you, and now I'm going to turn it over to Laurie Leshin.
Hey, thanks, Laurie. It is a pleasure to be with you today. Definitely bittersweet, but mostly incredibly celebratory. We are here to celebrate something extraordinary: Ingenuity's innovation, inspiration, and technological achievement. You know, I was actually in a meeting today on the Caltech campus talking about innovation and the need to be bold. And we were talking about what's often said about the 3 phases of a bold idea. First, it's ridiculed. Second, it's violently opposed. And third, it's accepted as being self-evident. And in this case, the bold idea was that we could fly a helicopter on Mars. And it definitely went through stages where nobody thought it was possible. And that's because on Earth, helicopters can't fly above about 25,000 feet. And on Mars, the atmosphere is so thin that it's equivalent to what Earth's atmosphere is at 80 or 90,000 feet. So clearly, this was impossible, right? It was an impossible task. And as the administrator said in his lovely video, our Mars team made the impossible possible. Hopefully, you would agree that it's worthwhile to draw a parallel with the Wright brothers. You know, the Wright flyer flew 4 times, only 4 times, on the first day of flight, which of course was an extraordinary capability that we still celebrate to this day. But it flew 4 times and then was blown over and broken by the wind at the end of the very first day of flights. Ginny lasted 3 years and flew 72 flights, and by any measure, it's a huge achievement. What I want to do is take a moment to acknowledge the brilliant team behind Ingenuity and say a special thank you to the great people who built and flew our first space helicopter. To accomplish a feat like this, it truly takes a team that, as we like to say at JPL, dares mighty things together. While we at the laboratory are honored to have built and managed and flown Ingenuity, great support and partnership was key across the agency and across partners outside of NASA. So I want to just acknowledge our broader team, including incredible support from NASA Science Mission Directorate, from NASA Ames Research Center and NASA Langley Research Center. Great collaboration across the agency. Also, our partners beyond NASA, AeroVironment, Qualcomm, and Sol Aero. They provided design assistance in major vehicle components, and also Lockheed Martin Space designed and manufactured the helicopter delivery system. So a huge, in some ways, a diverse team of organizations, but actually the team itself was quite small. It's a team of visionaries, pioneers, and engineers who are just crazy enough to think that this was possible. And it wasn't a huge team. At its peak in 2018, the total number of NASA team members working on Ingenuity was less than 50. I'm incredibly proud of the team. I give them huge kudos and congratulations, and I cannot wait to see what they invent next. I want to wrap up by talking about how Ingenuity's achievements paved the way to future missions at Mars and beyond. Technology demonstrations are incredible ways of proving new capability and painting a picture of the future. They can lead to awe-inspiring successes even beyond their own demonstrations, which are awe-inspiring. Sojourner rover was a tech demo. It led to the major successes and scientific discoveries of Spirit and Opportunity, whose 20-year anniversary of landing on Mars we are celebrating this month. Curiosity and now Perseverance, they all draw their lineage back to a tech demo that was Sojourner. And by the way, there's another very exciting tech demo being built right now at JPL, the coronagraph instrument for the Roman Space Telescope that is a pathfinder for taking family portraits of other solar systems, but looking for other habitable worlds. So Ingenuity was a tech demo that proved flight. It was an operational demo that showed how flight can complement other kinds of operational missions like rovers. And it was an engineering demo that showed how much higher, faster, and farther we can fly. It proved that flight was even possible on Mars. And I am excited to dream about future ways that we will use this capability on Mars and beyond. As I hand off to Teddy, I just want to highlight a few firsts again for you. First aircraft to execute a powered controlled flight on another world. First to take off and land under control. First aerial scout on another planet. And it was recognized appropriately with numerous awards, including the Collier Trophy, the Michael Collins Trophy from the Air and Space Museum, and the National Space Club's Robert Goddard Memorial Trophy. I hope everyone in the country is proud that our space agency creates an environment where innovations like Ingenuity are possible. We should not take that for granted, and we should really celebrate it. And just in closing, I look forward to the day that one of our astronauts brings home Ingenuity and we can all visit it in the Smithsonian. In the meantime, you can visit one of our pre-flight models there. So over to you, Teddy, to hear from the team.
Thanks, Laurie. I just want to start off by saying how incredibly proud and thankful I am to have worked with the amazing engineers, the technicians, our partners that you just heard about that made Ingenuity possible. Like Laurie mentioned, the Wright brothers come to mind when we think about Ingenuity. They unlocked the skies on Earth, made it commonplace to fly, part of our everyday lives. We all truly believe that Ingenuity has done the same for Mars, and it's now unlocked the aerial exploration dimension, and we couldn't be prouder of our little tough trailblazer. While Ingenuity is not going to fly again, new generations of Mars helicopters are on the drawing board. And we're excited for what the future will hold in the skies of Mars. In terms of what happened on Flight 72, there's a set of information that we know for certain. We've downlinked a set of images. The team has looked at those images and confirmed the shadow of one of our rotor blades suggests that our rotor blade is damaged, and that means that we're not going to be able to fly anymore. The good news is that we're still in communications with Ingenuity. And she's tougher, again, than any of us could have ever imagined. Going through a blade strike for a helicopter is typically the end. And Ingenuity was able to do that and still survive afterwards to phone home. We've been in communications with Ingenuity since the weekend, collecting additional data, and we're still in the process of getting additional imagery. We're interested in understanding how the other blades fared, how the rest of the subsystems are doing, but we couldn't be prouder of our little spacecraft. Ingenuity was aptly named. There were a lot of different elements that went into the design, the evolution, the testing here at NASA JPL, and of course the operations on the surface. One of the things that made Ingenuity possible was the use of commercial off-the-shelf parts. We have cell phone chips powering the thing. We have cell phone cameras, miniaturized electronics, off-the-shelf lithium-ion batteries, and the advancements over the last 2 decades of various industries is really what came together to make Ingenuity possible and to be an example for all of us of what we can do in the future. We can build things more affordably, quicker, and really pull off some amazing things. We also never planned for such a long mission. We originally had a single logbook, hoping for one successful flight to be logged in that logbook. Eventually got to 5, and we were extremely excited to proceed into our extended operations demonstration. We now have a fully packed logbook and a second volume of a logbook to capture all the rest, leading all the way up to now, finally, Flight 72. We've had amazing luck along the way. We can't forget that. We've been extremely lucky to be flying this long at Mars and to have to deal with cold winters, dust storms, and an infinite amount of curveballs that Mars always throws at you when you're trying to operate a spacecraft so far away. Again, I just want to express how proud we all are of our little aircraft and to celebrate the amazing successes that we've had. None of us should be surprised in the future when the first astronauts, the first women and men are on the surface, and we have fleets of aircraft flying around capturing those scenes. So thank you all very much.
Thank you all. So we can now go ahead and begin taking questions from media. So if you'd like to ask a question on the phone, you can enter that queue by pressing *1. And when you ask your question, please do let us know which speaker you're directing it to, if you know. And as a reminder again, in addition to the speakers that you just heard from, we also have Dave Lavery, our Ingenuity Program Executive, on the line. So we will go ahead now and take our first question from Bill Harwood with CBS News. Go ahead, Bill.
Hey, thanks very much, and congratulations on Ingenuity's legacy here. How far is Ingenuity from Perseverance right now? Is there any chance that at some point the rover can get closer to get a picture, or is it too far away? And is it 72 flights in all, including the one that you lost contact with? I mean, the press release said there was an emergency landing on the previous flight. I'm assuming that was Flight 71. And is there any information about that landing that you can share with us? Thanks.
Yes, so I'll handle each of those in succession. Currently, Perseverance is several hundred meters to the southeast of Ingenuity. It's on its journey driving west on its sample collection mission. We anticipate that the rover may be able to get within 200 to 300 meters away, and we're going to try and get some photography from Perseverance's perspective, but we don't anticipate it's going to be a very good image because of the distance. We will do our best and try, but it's going to be from several hundred meters away. The second question.
Yeah, it was just trying to get the flight sequence straight.
Yes. So Flight 71, correct. During Flight 71, we had an emergency landing due to the terrain. Where Ingenuity was flying around Flight 69, 70, 71, and finally 72, it's some of the hardest terrain we've ever had to navigate over. It's very featureless, and that's why we believe that during Flight 71, we had an emergency landing. She was flying around the surface and was realizing that there weren't too many rocks to look at or features to navigate from, and that's why Ingenuity called it emergency landing on her own. We believe the same thing happened on Flight 72, and finally, the full count of the flights is 72, including the final flight.
Thank you.
All right, thank you both. Our next question here is from Mike Wall with Space.com. Go ahead, Mike.
Just wanted to say thank you and also congratulations. I'm going to miss Ingenuity, and yeah, kind of keeping tabs on it, just like all of us have been. This is probably for Teddy. Do you know exactly what happened to the rotor? Did Ginny come down and just kind of clip the ground with the rotor? Is that what you think happened? And could you give like a little update maybe about what the next few generations of Mars helicopters might look like, and what sort of research is sort of going on that end at JPL and other places around the country?
Yeah, so first, in terms of what happened precisely on Flight 72, because we lost communications with the helicopter during descent, the full high-rate data log that we typically get during flights is not available. We won't be able to get that log back.
Okay.
It wasn't saved to disk. As a result of that, we won't know for certain. However, all of our engineering judgment leads us to believe that during descent, we had a blade strike with the surface of Mars. We believe it was our lower rotor system. Again, in the coming days, we'll try and get additional imagery to confirm that. And at least one of our rotors, the last 25% of the length of that rotor blade itself, is missing in the shadow. Whether or not the blade strike occurred, which led to the communications loss, or there was a communications loss and a power brownout, which then led to the rotor strike, we will never know. But the team is still going to try and piece together more data in the days ahead here. In terms of the other helicopters, There are future generations that we're planning here at NASA JPL to do more challenging things, carry heavier payloads. There are Mars science hexacopters that are in research concepts that are in publications you can look at, and the existing efforts here going on lab for the sample recovery helicopters. But that's all future-looking concepts.
Thank you.
All right, thank you. Our next question is from Steve Gorman with Reuters. Steve, are you able to hear us? All right, we may need to come back to Steve here. So we can go ahead and take our next question from Eric Berger with Ars Technica. Eric, are you on the line? We may be having a technical issue with our Q&A at the moment. Well, while we address that, just as a reminder, if you'd like to get into that queue, you can press *1 to ask a question, and we will try here to come back to our questions that are in the queue currently. All right, so let's give it another try. Are we able? Oh, it looks like we actually have to clear our queue for the moment, so we apologize. If you wouldn't mind pressing *1 to get back into that queue to ask your question, we'll be able to come back to you here. So I'll give everyone a moment who is interested in asking a question to press *1.
Elise, this is Laurie, and while we're waiting for folks to get queued back up, and you were thinking about, there was a question about future helicopter developments, I want to take the opportunity just to mention that, we do have in work another aerial vehicle being developed for exploration of Titan, a very, very different environment, atmospheric environment, but we're really excited to see, the growth of this new kind of approach to exploration, kind of spearheaded by Ingenuity.
Thanks so much, Laurie. Appreciate it.
Thanks.
And it looks like we now are back up and running on our Q&A here. So again, apologies if you were in the queue here to ask a question. Please do press *1 again, and we'll add you back here. All right, so we can take our first question from those who are back in the queue. That will be coming from, I'll give it a moment here. All right, that will be coming from Marcia Dunn with the Associated Press. Please go ahead, Marcia, and thanks for the patience.
Yes, hi. You said that you think one of the blades may have struck the surface of Mars as it was coming back down. Do you think that more than one blade was damaged in the end, or do you think the damage is limited to just the one that may have struck the surface of Mars?
So our rotor blades spin at 2,537 revolutions per minute, incredibly fast. There's a good chance, given the rotational rate, that multiple sides of the rotor system impacted the surface. Currently, we only have photo evidence of a single shadow for a single blade. Again, the team in the coming days is going to try and spin the blades as best they can and try and get images of the other side, but it's likely.
Thank you.
Thank you both. We can take our next question from Kenneth Chang with the New York Times.
Hi, thank you. This is for Teddy. What was the reaction of you and the others in the team when you saw that shadow of the broken blade? Obviously, you're not surprised, but on the other hand, it seems like this was going to go on forever.
Yeah. I'm sure, as anyone could imagine, it's bittersweet for a moment there, because you got to remember, this entire team prepared for a tech demo. It was supposed to be 30 days, right? So emotionally, for the last 2.5 years, we've been prepared for a sprint, and then we had to transition to a marathon, right? And we've been now in a marathon mode, and there's always that piece in the back of your head that's getting ready every downlink. You know, today could be the last day. Today could be the last day. So there was the initial moment, obviously, of sadness, seeing that photo come down and pop on screen, which gives us certainty of what occurred. But that's very quickly replaced with happiness and pride and, a feeling of celebration for what we've pulled off. It's really remarkable, the journey that she's been on, and worth celebrating every single one of those souls. I do want to mention that as of around 9 p.m. tonight, Pacific, will mark 1,000 souls that Ingenuity has been on the surface since deployment from the Perseverance rover. So she picked a very fitting time to come to the end of the mission here.
Thank you. For our next question, we can go back to Eric Berger with Ars Technica. Go ahead, Eric.
Hi, can you hear me now?
We can hear you now. Thank you.
Excellent. Thank you. I wanted to echo others who have just congratulated NASA on such an inspiring and amazing mission. I wanted to ask about what's coming next. I know Laurie mentioned the Titan mission, and you've got possibly the sample return helicopters and other things like that. But just big picture, what have you learned from this tech demo about the capability of flying on Mars and potentially other worlds? How much more is that going to factor into robotic missions that NASA is planning as it looks at other bodies in the solar system? Thanks very much.
Sure. So this is Laurie Glaze, and I think Laurie Leshin kind of alluded to this at the beginning, right? That as we went with the Sojourner rover, it's just really grown how we think about not just Mars, but the rest of the solar system. Even though we don't have rovers on other planets necessarily, we're thinking about how important it is to have that mobility and that roving capability. And I think that this aerial capability is going to be the same. It'll be, this demonstration on Mars showed us what we can do in that operational mode where we're working in tandem with a rover, and a more capable helicopter such as those that Teddy says are being worked on at JPL that can carry heavier payloads, could go visit places on the surface that the rover can't visit, or can scope out and help us identify places that we really want to send the rover, or actually do all the exploration themselves within the helicopter. And again, thinking of the Dragonfly mission at Titan, where the helicopter is in fact the main science explorer. It will be hopping and traversing over about 100 kilometers on the surface of Titan and collecting data at multiple locations on the surface using aerial mobility as opposed to driving. And we've talked about also the importance that when we send humans to Mars, the helicopters can again potentially really have to expedite and make our the sorties of the astronauts more efficient, being able to collect samples or things from the surface and bring back to the astronauts, or work with the astronauts in tandem. So I think now that we know this capability is possible, we'll push the boundaries of what we can.
On the engineering side, every single flight has given us a treasure trove of data that we've been collecting, and that will form the foundation of any future design efforts between aerodynamics information, thermal modeling, structural modeling. Ingenuity was based off of theories. We now have facts, and future aircraft designs are going to rely on all the data we've collected from Ingenuity.
And I'll just add one more. This is Laurie Leshin. As a Mars scientist myself, I dream of a helicopter exploring the canyons of Valles Marineris, right? As Laurie said, this type of mobility can take us to places that we have never dreamed we'd be able to explore on Mars. And the possibilities are really endless.
Thank you all. Our next question is from Jackie Goddard with the Times of London.
Hello, thank you, and congratulations. My question is for Teddy. It builds a little on an earlier question. I wanted to explore a little more that relationship that humans have with your gadgetry up on Mars, with your robots, because there's a lot to celebrate in terms of accomplishment, but this is also a loss. So I wondered if you could elaborate a bit more on what this means to the team emotionally. This isn't just a piece of hardware. You have that kind of daily relationship with this little thing on Mars, and that's now gone. Could you just talk us through a little more of that emotional side and how it unfolded and what people have been doing to kind of cope and wind down from the intensity of the emotional side? Thank you.
Absolutely. You could imagine working on anything for 2.5 years. You start to build up a personality for whatever you're working on. I definitely feel, and I'm pretty sure most of the members of the team feel, that Ingenuity has formed a personality on the surface of Mars, and we've learned about the ins and outs of that since Flight 1, through the tech demo of Flight 5, and now all the way through 72. Those quirks stay with you, right? And you remember exactly the nuances of what temperature you need to wake up on and preheat to, and all the details of planning a flight, as if it's a member of your own family, right? It's a part that will stay with us. Keeping that with you over 2.5 years of extended operations, and now that we're coming to the end here, it's important that we all, take a step back and get the perspective on exactly how lucky we've been, right, and fortunate we've been to be able to work on this, and understand the magnitude that Ingenuity is going to have in its impact for humanity, for space exploration, for robotics in the future ahead. So, in one word, it's really just appreciation for everything that we've been able to do with this little helicopter.
Thank you.
Thank you. Our next question here we'll take from Ryan Caton with NASASpaceflight.com.
Hey, thanks for taking my question. This is, I believe, probably to Teddy. Does Ingenuity have the ability to serve as a stationary science mission, like as a lander, kind of like InSight, that kind of style mission in the future?
There are no science payloads on Ingenuity itself, right? Ingenuity is a technology demonstration aircraft. It carries no additional payloads. We are interested in trying to collect as much data as we can as the Perseverance rover continues on its important mission to the west. And eventually, as the rover drives to the west up the crater rim at Jezero, we will lose contact, right? And that will happen in the days, weeks, and months ahead of us here, depending on the rover's plans. Once that happens, any hope to get additional information back from Ingenuity is gone. We won't be able to communicate. During that time, we'll collect solar panel measurements, we'll collect thermal measurements, we will also correlate our telecom radio strength, and there's information you can glean from that to improve models, and especially the images, also may be interesting to geologists and scientists. But that's effectively it.
All right. Our next question comes from Ashley Strickland with CNN.
Hi there. I just wanted to echo the congratulations. It's been so wonderful following the journey of Ingenuity these last few years. Teddy, my question is for you. I wanted to ask, what have been some of the biggest lessons learned that could give us to future tech demos that seem impossible at first, just like Ingenuity did?
Yeah, absolutely. So I'll start big picture, and then I'll narrow down to some specific examples. I think one of the biggest lessons learned is teaching ourselves at JPL and throughout NASA that this technology demo way of doing things works and is resilient and is reliable. We developed Ingenuity, right? It was supposed to be a high-risk, low-budget, rapid schedule development, and we relied on commercial off-the-shelf parts to get that done. That is a massive victory for future mission planners, mission designers, because they can rely on what we've accomplished. They can point to the fact that a cell phone processor from 2015 can survive the radiation environment on Mars for 2.5 years. Lithium-ion battery cells that are commercial off the shelf can survive for 2.5 years, right? Those are massive victories for engineers around NASA, and I'm certain that we're going to carry those examples forward for any future mission we plan.
Okay, we'll take our next question from Irene Klotz with Aviation Week. Go ahead, Irene.
I have two questions, science and then engineering. The science question for whoever is closest to mission planning. I wanted to know how the loss of Ingenuity might impact the ongoing Perseverance mission. And the engineering question is, I'm a little confused about the sequence of events. So comms were lost, and if you have the how far above the ground the helicopter was at the time, and then comms were regained once Ingenuity was on the ground, and how long a period of time was it out of comms? Thanks.
In terms of the first question, any science impact? None. As stated earlier, there is no science payload on Ingenuity as a technology demonstrator. So there will be no change to the science return. In terms of aerial imaging and scouting, obviously there's various benefits to that. But for the core science campaign of Perseverance, none. Just to recap the timeline of events, starting with Flight 70, we were flying to the northwest in this area of the crater rim, or on our way to the crater rim, and we started flying over some of the most challenging from a feature density perspective. That means bland, sandy terrain, right? We saw that in Flight 70. In Flight 71, we were trying to get through that, had an emergency landing, but we're safe, right? We got down to the ground and we established that the rotorcraft was still healthy and able to fly. Then again in Flight 72, we tried doing a pop-up, a simple, about 30-second flight, where we just wanted to take off and come back down and land. During landing, the helicopter was on its way down for descent. We have reason to believe that the same featureless terrain challenges were being faced by the helicopter. And during descent, we lost communications with the helicopter. We believe that what happened is the helicopter was landing back down on the sandy terrain, and because of the navigation challenges, we had a rotor strike with the surface. That would have resulted in a power brownout, which caused the communications loss. And that's why immediately on that flight downlink, we weren't able to see our full data. The next Sol uplink cycle, we tried communicating with the helicopter, and she was right there where we expected her to be in terms of time. We got information back. She replied back that solar panel currents were looking good, which indicated that she was upright, and we tried collecting as much data as we could. But as I mentioned earlier, we're not able to get the data from the seconds of descent that we lost. That information's we're not able to get that data back. So we're piecing together the bits of information we have to formulate that timeline.
All right, thank you, Teddy. Next, we have a question from Evan Ackerman with IEEE Spectrum.
Hi, thank you very much, and congratulations to the Ingenuity team for setting an impossible standard in the tradition of JPL spacecraft. I have a couple questions for Teddy. The first one is that even for robots on Earth, navigating in featureless places is a real challenge, and I'm wondering if you have any thoughts about how future rotorcraft on Mars might be able to solve that. And then secondly, I'm just curious, I would guess that Ingenuity's first few flights will always be the most special, but I'm wondering if over the past 50 or so flights, one in particular stands out to you in some way.
So for the first part of your question, I'm actually going to pass off to Håvard Grip, who is our Ingenuity Chief Pilot Emeritus. So Håvard, do you want to take that first question, and then I'll take the second?
Sure, yeah. So, overall, the way that Ingenuity has navigated using features of terrain, it's been incredibly successful. We didn't design this system to handle this kind of terrain, but it's nonetheless, it's sort of been invincible until this moment where we flew into this completely bland terrain where we just have nothing to really hold on to.
And so there are some lessons in that for us. We now know that that particular kind of terrain can be a trap for a system like this. We know things that, features that the helicopter could have had to, had we predicted this ahead of time, like backing up again, when it encountered this featureless terrain. That's a functionality that a future helicopter could be equipped with. And then there are just, solutions like having a higher resolution camera. Higher resolution camera would have likely, helped mitigate this situation. But it's all part of this tech demo, where we equipped this helicopter to do at most 5 flights in a pre-scouted area. That was the whole idea. And it's gone on to do so much more than that. And we worked it all the way up to the line and just tipped it right over the line to where it, couldn't handle it anymore.
In terms of the second part, the most harrowing activity is actually not a flight for me. We had practiced flying the helicopter in chambers here at JPL dozens of times, and the team got very good at that, testing it out in our chambers here. The most stressful part for me personally was actually deployment. We did an activity called drop and drive, where we had a handful of minutes with controllers here on the ground on Earth to either override or force the rover to drive over the helicopter to make sure that the solar panel was being hit with sunlight. And had we missed that opportunity, those handful of minutes in commanding time, that could have spelled the end of the tech demo before we ever started. So that was the most stressful moment for the entire mission for me.
All right, our next question here is from Jeff Faust with Space News.
Hi, question for Teddy. Beyond the damage to the rotor, have you seen any signs of any other damage or degraded systems on Ingenuity after the landing? Thanks.
Aside from the shadow image of the rotor system, no, there's no further damage observed as a result of our rough landing here with Flight 72. Over the last 2.5 years, we've been closely monitoring the progression of the health of the vehicle, and I'm extremely proud to say that she's effectively green across the board. We've lost one inclinometer sensor, not flight critical, in our first winter, and the rest of the subsystems from the solar panel to the battery has been aging remarkably well. Our electronics, avionics, processor all seem to be doing just fine.
Thanks, Teddy. We'll take our next question now from Marcia Smith with Space Policy Online. Go ahead, Marcia.
Thanks so much. I have 2 questions, and I think they're probably for the 2 Lauries. One is sort of a broad question about technology demonstrations and how NASA views them differently from traditional missions. Is it that the tech demos are higher risk but lower cost, and how do you decide that something's going to be a tech demo instead of part of the critical mission? And then the other question is, you've been talking about how this feeds forward, and of course you're going to have 2 similar helicopters on the Mars sample return mission. So which of the lessons that you've learned from Ingenuity will be applied to those, like maybe having high-resolution cameras, and will those fly over where Ingenuity is on their way to pick up the samples?
So, Laurie, Glaze, would you like to jump in on those?
Yeah, I will. So you're asking some questions about, technology demonstrations and, how we think about them. Certainly, we are willing to accept significantly higher risk. We generally, use somewhat lower investments. You heard Laurie at the beginning say that this was a small, tight team working very closely together over a rapid time frame. And so the idea is to try and see what we can do in these technology demonstrations, kind of push the boundaries and accept risk. We also, for something like Ingenuity, where we're flying it along with another primary mission, we have, rules of do no harm, where we definitely want to try out the technology, but we always keep in mind that the primary mission is the main goal. So we do everything we can to do the technology, but we also want to make sure that there aren't any new requirements that are placed on the primary mission. And, I think Ingenuity was a great example of that. We did have to accommodate Ingenuity onto the belly of Perseverance and then develop the sequence for dropping it on the surface, and then, of course, the communication pathway, but they ended up working together extremely well. And as far as the future, as you are likely aware, we are in the middle right now of assessing the architecture for Mars sample return. We instituted an independent review board over the last summer, and they released their report in the fall and suggested that we go back and relook at architectures. So right now we're in the middle of the response to that independent review board, and so I think at this point, we're still kind of in the middle of that process and not quite ready to talk about what the Mars sample return architecture that we move forward with, the specifics of that at this time.
Can I just jump in on the tech demo part slightly? Yes. I love what Laurie said. This is the other Laurie Leshin. I do just want to, emphasize the importance of these kind of missions, both historically and in the future. And another great example that I'll give is the Deep Space Optical Communications demo, flying aboard Psyche. It's another good example where it was, on a non-interference basis, and it was a relatively constrained team, and it is revolutionizing the way we communicate from deep space. And these missions lay the foundation for a bright future. And it's so critically important that we continue to look for places, look for opportunities to fly these things, to get that flight experience, to prove out these capabilities. And it's, we have a lot of launches these days, which is great, which should give us, one of the great things about the reduction in launch costs and the much wider availability of launch is that it should allow us to do more of this. And, like one of our colleagues in the media said, people love these demos. They love to see how we can push the boundaries. So I think it's really important that both through SMD and the Space Technology Mission Directorate that we keep pushing to do more tech demos.
Thank you both. Next, we have Leo Enright with Irish TV.
Thanks very much for doing this, and congratulations on this remarkable mission. Talking about tech demos, I've been up since 5 o'clock this morning here in Europe with another tech demo, the Japanese one, the SMART mission, Japanese mission to the moon. And I wondered if Laurie Glaze had any words of wisdom from NASA, who certainly have had 2 spectacularly successful demonstration missions to Mars with this mission and also the Sojourner rover. And if I could also, a second question to Teddy about the imagery that's been coming down just recently from the helicopter. The footage from Sol 1040 it seems to show a huge divot in the sand. And I just wondered, is that divot a hole made by the rotors?
Leo, thank you for the questions. This is Laurie Glaze. I'll take your first one. We've also been following very, very closely the JAXA SLIM mission, their SMART lander. I just want to take a moment to really congratulate them on the soft landing on the surface of the moon. That is an incredible feat in and of itself. We know that everything didn't go quite according the way they would had designed, but they had a number of major successes, and I believe they're going to be talking about those publicly pretty soon. Very good, a lot of great successes on that mission. I also wanted to mention we've talked about Ingenuity, and we've talked about DSOC. And these are investments that JPL is investing in. I want to also make sure we give a shout out to the 2 CubeSats, the Marcos, that that launched with InSight, and were able to provide real-time communication relay. And these are technologies that our NASA centers and others are investing in on a continuous basis, either through NASA programs or through their independent funding at their centers. And those are the kinds of things that we invest in over time, and it's great to see when those investments really pay off with these tech demos. And I'll pass it over to Teddy to answer the other question.
Thank you. In terms of that, I think divot you called it, right? We don't know for certain. It could be that was the result of the blade strike itself. It could also be that as the helicopter was coming down, you can see in the image where the feet are resting, that there was some side slip or some side motion from the feet. So it could be that one of the helicopter legs was dragging in the sand as it was coming to a rest. We are not certain. We're going to try and collect additional imagery again in the coming days, but it's hard to know for certain if that feature was there before we even arrived, if we created it with a blade, or if we created it with a foot.
Thank you both. I will take our next question here from Rick Lovett, who's freelance. Go ahead, Rick. Rick, if you are speaking, you are on mute.
Oh, sorry. It won't unmute.
Hi, Rick. We can hear you now. All right. Sounds like maybe Rick is unable to hear us, so we can maybe come back to him.
Can you hear me now?
Oh, yes. There you go. Hi, Rick.
I'm sorry. It would not unmute. Now it did. So my question is, sorry for the delay there, over a featureless terrain like this, how exactly did it wind up hitting a blade on the ground? Did it land on a slant that it couldn't detect, or was it unable to keep its vertical orientation as it was coming down? Or, I mean, these are by theory, hypotheses, but I'm kind of curious what would have gone wrong.
So I'm going to this is Teddy Tzanetos. I'm going to pass the question to our Chief Pilot Emeritus, Havard Grip, to answer that.
Yeah, so some of it, becomes speculation because of the sparse telemetry that we have from landing. But we can say in general is any system where you track features in order to navigate, it's going to see a lot of different features, and some of them are going to be good features, some of them are going to be bad features. And the way a system like this works is by looking at the consensus of what it sees and then throwing out the things that don't really agree with the consensus. And the danger is when you run out of features, you don't have very many to navigate on this, that you're not really able to establish what that consensus is, and you end up tracking the wrong kinds of features. And that's when things can get off track. And so what we see in the telemetry is that coming down towards the last part of the flight on descent, when you're closing in on the ground, that the helicopter relatively quickly starts to think that it's horizontally moving away from the target that it's landing at. And so it's likely that it made an aggressive maneuver to try to correct that right upon landing. And that would have accounted for sideways motion and tilt of the helicopter that could have led to either striking the blade to the ground and then losing power, or making a maneuver that was aggressive enough to lose power before touching on the ground and then striking the blade. We don't know those details yet. We may never know, but we're trying as hard as we can with the data that we have to figure out those details.
Thank you. We have time for just a couple more questions here. So we'll take our next one. This is another question from Kenneth Chang with the New York Times. Go ahead, Kenneth.
Sorry about that, I was muted.
Oh, there you go. Hi there.
I was wondering if someone could give me an example of how Ingenuity aided the operations of Perseverance, and how the Perseverance mission might be changed now that you no longer have an aerial scout?
So I'll answer the second part first, which is there won't be a change to the Perseverance mission. Ingenuity was a technology demonstrator, and because of that, there was no part of Perseverance's core science mission objectives that were dependent on Ingenuity at all. So Perseverance is going to keep doing its thing and drive west and collect the important samples to bring back home to Earth. In terms of the first question, what has Ingenuity done to contribute? There are a handful of great examples of what what really having any aircraft at Mars does for scientists here on the ground and rover planners. You can look back at Flight 13 when we imaged Phaefu and created a three-dimensional map that was of interest to scientists to be able to see for the first time ever a 3D map from the aerial perspective. There's also a handful of examples where we sent Ingenuity ahead of Perseverance to try and get some scouting imagery of the drive path so that rover planners could look at it early before Perseverance got there and try and assess, is path A safe or should we go down path B? And those handfuls of examples, lead us to believe that, there's only more and more value for future missions, either with larger rovers or eventually once we send humans to Mars to have that aerial dimension available to us.
Thank you. Our next question here is from Irene Klotz with Aviation Week.
Thank you. For Laurie, Glaze, are you saying that it's a possibility that the helicopters could be eliminated from the Mars sample return architecture?
The independent review board report that was released suggested that we should go back and reconsider all aspects of the architecture, and that's the process that we're undergoing right now.
Thank you both. And our next question is from Steve Gorman with Reuters.
Hi, thanks for coming back to me. So just to make sure I understand, it sounds like that what we think happened as this helicopter was coming down, making its descent in this featureless environment and trying to navigate the best it could in this feature, that it may have lost some of its own equilibrium. Or attitude control, sort of experiencing aeronautical vertigo, if you will, as it was descending, and that may have caused it to tip or tilt in a way that caused it either to lose power or strike the ground. Is that right?
Yes, that's a accurate summary of what we believe happened.
All right, and next up we have Bill Harwood with CBS News.
Yeah, hi. Just a really dumb question from the peanut gallery. Given the one picture we've seen, the shadow and the tip of the blade, do you know for certain that if you spun this thing up, it couldn't possibly fly given just that one rotor's damage, or is it really the assumption that, you have more than one rotor, like as you said, likely damaged, and that a flight would not be possible? I'm just curious how you know you can't fly anymore. Thanks.
So our engineering judgment is what leads us to that conclusion based off of a couple of facts. Ingenuity's rotor system is impeccably well balanced, down to the fraction of a gram. And when you have not just Ingenuity's rotor system, but any helicopter system, it must be perfectly balanced. Otherwise, any rotor system will shake itself apart. If anything compromises the delicate balance of a rotor system like that, and then you start trying to spin it at 2,500 RPMs, you're not going to be able to sustain that for any reasonable period of time. That's one reason why. The second reason why is just the aerodynamics and the physics of it. Most of your lift comes from the last 25 to 35% of your rotor system. It's the fastest moving part of your blade as it rotates in a circle. Because we think we've lost about 25% of one of the blades, that means we've just lost a massive chunk of our thrust capacity. So even if the blades were somehow perfectly well balanced in their damaged state, we've now also just taken a huge chunk away of our thrust capacity, not to mention the controllability of being able to handle small roll and pitch maneuvers in air with now your control surface being compromised. So all of that leads us to believe that we will not be able to fly anymore.
Thank you, Teddy. And with that, that is all the time that we have for questions today. So if you had a question that we didn't have the chance to get to, please do reach out to NASA's media team. But thank you again to our speakers and to everybody who joined us as we celebrate this incredible mission. And to learn more about Ingenuity and the Mars 2020 mission, you can visit mars.nasa.gov/Mars2020. Thanks again.
This does conclude today's conference call. We thank you all for participating. You may now disconnect and have a great rest of your day.